we're all in the same room together. The only thing I'd ask is that just to avoid too much distraction is keep your microphones muted. But if you want to ask a question, just go ahead and unmute your microphone and go ahead and ask your question. Go ahead and just interrupt me and I'll do the best I can. So I've been retired for a while, but I was lucky in my career. I was just kind of amazing that my ham radio background as a teenager and then through college wound up through a whole series of accidents being a very excellent match to what my professional career wound up being. For a lot of my career, I worked on military space programs as a systems engineer. And one of the aspects of system engineering that's very important is understanding as much as you can about the totality of the environment that the systems operate in. And of course, if you're dealing with space systems, then you're dealing with the sun and everything that goes on in interplanetary space and the ionosphere and particles and on and on and on. So it was during my engineering career that I was fortunate to be able to get to know some of these people who are experts in this area, and I was able to absorb a little bit of information from them. Many of these people were physicists who had worked in these areas of science for their whole careers, so they were very patient with me. Let's just leave it at that. But I learned a lot from them. So let's go ahead and talk about solar maximum. We're right in the middle of solar maximum right now. And you know, I can't tell you how many times hams mentioned to me that they'll probably never live to see a really big solar maximum again. But for all of us that are alive, here we are. And this is a remarkable solar maximum. This normally the summers for normal sunspot cycles, fairly weak ones, which we've had for the last 20 years. Usually the summer is really kind of the doldrums. But 20, 15, and 10 meters are open all night long. And I'm kind of a night owl. That started when I was in college and I worked for a TV station on the engineering staff. I worked nights. And back in those days, 50 years ago, TV stations shut down at night. Now they're 24-hour day operations. So I was always on the crew that shut down the TV station at 1 a.m. And those habits stuck with me. So I've been a night owl ever since I was in college. So I've been enjoying the HF bands at night. They're just amazing. You flip on the 20-meter band or the 15-meter band and the 10-meter, well, not so much 10 meters at night, but 20, 17, and 15 meters. You turn your radio on at any time of the night, and there's going to be some kind of DX propagation coming in from somewhere. It's just kind of amazing when you're used to having those bands dead at night. So this is an article I published in May QST last year. We were kind of discussing what solar maximum might be like, and the article discusses what it might be like. Well, it turned out that what I discussed a year ago in this article was pretty accurate until July of this year. And then suddenly, the solar activity skyrocketed in July, and it's continuing right up to today. We don't know if it's going to calm down from where it is now or if it's going to continue to get higher. But the good news is that it has really opened the bands this summer, and it's been a lot of fun. I have another article. I was asked by the editors of QST, once the solar cycle started to heat up in July, if I could put together a quick article to appear at October QST, and I wrote it, and they said, yeah, this is exactly what we wanted. So in about a month's time, the digital version of QST will show up on the NORL webpage, and the printed version will be right on its heels. These are, for those people interested in pursuing a little more detail, all three of these books were written for hams. And in all three cases, they were written by people like myself who had professional careers related to this. So we have quite a lot of in-depth knowledge among the various people that contributed to these books. The one on the right, Here to There, Radio Wave Propagation, is not a very expensive book. It's about $20, and it's very current, just published in the last year. The other two books are reference books, and they have a lot of detail. And they both deserve a spot on your bookshelf if you're so inclined, but they're much more expensive than the one on the right. By the way, I'm going to leave a copy of this presentation with Bill, K2TNO, so hopefully if you're interested, you can get a copy from him. So you don't have to worry about writing anything down. You'll be able to get a copy of it. This is a very detailed publication that was written by a physicist for physicists. So it's kind of hard for most hams with a non-technical background to kind of wade their way through this. But the good news is that it's free. You can go right to the webpage and get the book, and it has a very good index at the back of the book, so you can look up individual topics and so on. So it's worth looking at if you're so inclined, but be prepared to be kind of buried in technical mumbo jumbo that most hams don't try to dig their way through. So this is kind of a top level summary of some of the terms involved in understanding the relationship between the sun and interplanetary space and the ionosphere and propagation. And anybody that pays attention to this stuff has probably heard all these terms. The sun has a very powerful magnetic field, much, much, much more powerful than the magnetic field on the Earth. And that field extends all the way through the solar system to the Earth and well beyond. The sunspots we see are in the sun's corona, which is an amazingly hot region of the sun, millions of degrees. It's just hard to put your hands around some of these concepts that just don't make any sense to humans, but the temperature is just unbelievably hot, and scientists haven't really figured out why it's so hot, but it's just incredible. Many of us have heard about sunspots. Well, they live in regions that also emanate solar flares and something called coronal mass ejections. And those regions are called active regions. They're areas of intense magnetic fields on the sun. Sunspots, the magnetic fields from sunspots are closed magnetic fields. They don't extend far out into space. Whereas opposing that for coronal mass ejections, the magnetic fields extend far out into space and have a big effect on this, on the Earth and on our propagation. The solar cycle is nominally 11 years, but that could vary from about 9 years to 14 years. We don't know how long this solar cycle is going to last. It seems to be on track for about an 11-year cycle. But now that this cycle has gotten to be much stronger than we expected, it would be wonderful if it extends itself out beyond 11 years. I hope it does. And another thing that's just kind of amazing is some of this terminology. That the solar wind carries megatons per second of magnetized particles out into space. And you might think, my God, is this a problem? Megatons per second? How long can this last? Well, it's been going on for billions of years, and it's had almost no effect. Megatons per second is just insignificant compared to the mass of the sun. So these terms you hear associated with solar physics are just kind of astounding. Some of you may have heard the term coronal holes, and we'll talk about that briefly in the presentation. Coronal mass ejections are explosions of highly magnetized particles, and they have a big negative effect on propagation. And solar flares, we'll talk about that in a little bit. So these are the terms that they're kind of basic terms associated with propagation. A lot of hams have only heard about sunspots, but all of this stuff is important. And maybe most hams have heard about the solar cycle. I'm not going to read all of this. The presentation will be available to those who want to look at it. But I'll just briefly mention a couple of words about each one. Sunspots are what cause the enhancement to solar propagation. They vary with the solar cycle, which is nominally of 11 years, but it can be as short as 9 or as long as 14 years. The radiation from sunspots that causes enhanced HF propagation is called extreme ultraviolet radiation. So it's the same kind of UV that will cook you on the beach, but it's at a different wavelength, which fortunately is completely absorbed by the atmosphere of the Earth. And if it weren't, there wouldn't be any human beings on this Earth that could possibly survive the strength of this radiation. But this is the radiation that ionizes the atmosphere. And just as an aside, in the process of ionizing the particles in the atmosphere, creating the ionosphere, that process creates extreme heat. And that is what causes the area of space where satellites, low orbiting satellites, and the space station is located to be in a very hot environment. It's the process of ionization that causes all that heat. Totally unrelated to, well, almost totally unrelated to HF propagation. It turns out that heat also creates winds at those extreme high altitudes, and that does affect propagation to some degree. So the sunspot cycle isn't all about good news. Along with enhanced propagation like we're having right now, especially on 20, 17, 15, 12, and 10 meters, we're also getting some very disturbed days. And those are caused by disturbances to the Earth's geomagnetic field, and that magnetism has a big effect on the ionosphere and causes some pretty bad propagation. But usually these disturbances last only a day or two, and things are back to normal, and the good times are back. So just like the Earth, the sun also rotates, but its rotation period, as observed from the Earth, is about 27 days. So some of the really good days that you might observe on the HF bands is a very good chance that 27 days later, you'll have some more really good days. And on the contrary side, on some of these days that are very, very bad, and normally about 5 days out of the month are disturbed, those days tend to repeat on 27-day increments as well. So there are kind of 3 major effects on HF propagation. One is ionizing radiation. So that comes from sunspots. That's very important and very beneficial. The other is seasonal variability. You know, the Earth has 4 seasons, and those seasons are caused because the Earth is tilted 23.5 degrees with respect to the Sun-Earth line. So when the northern hemisphere, we all of us live, is tilted towards the sun, like it is right now, the ionosphere gets a lot more ionization, and that has good effects and bad effects. And contrary to that, in the winter, the northern hemisphere is not pointing directly towards the sun. It's tilted 23.5 degrees away from it. So that causes very different propagation in the winter. And then there are the equinox seasons, where the entire Earth has just about the same exposure to the sun, and that causes another very different kind of seasonal effect on propagation. So the seasons that affect the weather on the Earth also affect HF propagation in a very big way. This illustration, and that's all that it is an illustration, kind of shows what the sun looks like viewed. These images are actually taken from a satellite. And you can see as you go through a sunspot cycle how the activity on the sun varies. And right at the center bottom shows roughly what the sun looked like in 2024. And when this slide was created, no one knew that 2025 was going to be even more active than 2024, or likely to be more active. So it shows it declining, but it might be about the same. We just don't know. This real heavy activity, very strong activity in solar activity started in July, just about 6 weeks ago. So we don't know if it's going to tail off at the end of this year or if it might even strengthen in 2025. Most of us think that's not likely, but you just don't know. There are limitations to our ability to forecast what's happening on a star that's billions of years old, and we've only been observing it with modern instruments for a few decades. So this is a forecast of solar flux. Solar flux is a measure of beneficial ionization from the sun. And this comes from NASA, the Marshall Space Flight Center. And it shows 4 different alternative propagations. The blue one appears to be on track to about what's happening on the sun now. I purposely did not show the updated version of this slide. There is an August 2024 version, but it's more pessimistic than this. And I think when they release the next version of this in September, it's going to look more like this version because of this very unexpected increase in sunspot activity. So the important thing in this slide is that we hear about solar maximum, and to some scientists, they think about solar maximum as a date, maybe a month and a year. But for hams, what's important is whether the amount of solar flux, the ionizing radiation, is above a certain threshold. And for HF operators, we like to see the solar flux in terms of 10-meter propagation to be up around 150, 160. And you can see for the purple and the blue lines, it would be well above that. Well, since July, it's been above 200, way up at the top of the chart is where it's been for the last 6 weeks, way above this forecast. So what's important is how long is it likely to stay elevated? And if you look at these charts, it appears that from these forecasts, and they're only forecasts, it appears that we might have about 2 more years of really interesting propagation on the HF bands. Time will tell, but it's very likely that we're going to have about 2 more years of this very interesting HF propagation.
Question, Frank?
Yeah, go ahead.
Yeah, this is Bill, K2TNO. Could you comment before you get off of this slide, since you've been through this so many times, what is it going to be like for ham operators down in 2030, when it's right at the minimum? Can you still talk to people on HF? Thank you.
Yeah, Bill. Of course, when were you first licensed?
1870, no, 1956.
So you've been through a few of these cycles. Well, the simple answer is HF propagation lives on. But what happens is that the higher HF bands are not anywhere near as good as they are right now. Right now, 20 meters is open all night, 15 meters is open all night, 17 meters is open all night, and that's going to be a distant memory, and long before 2031. So what will be happening then is if you are a 160-meter enthusiast, you're going to be very happy that all of this annoying sunspot activity is gone. The guys that like 160 meters do not like all this sunspot activity. It's not good for their interests on that band. And even the 40-meter band, which at this part of the sunspot cycle, it's open all night long for DX. But when we get near the bottom of the sunspot cycle, sometimes even in the middle of the night in the winter, 40 meters fades away. But you know, that's another 5 years before that gets to be much of a problem. But the important takeaway from this presentation, which is about solar maximum, is we've got about 2 more years to go of really good propagation, and then we're going to slowly decline in this cycle. And another thing to notice on this chart is notice how much more slowly the cycle declines on the right-hand side of this chart compared to how rapidly it rises. This solar cycle didn't really take off until 2 years ago, and here we are at solar maximum or very close to it. But it's going to take another 6-7 years for us to get back down to very low numbers. Okay. Another interesting aspect of the sun, of course, the sun has a northern hemisphere and a southern hemisphere, just like the Earth does. But curiously, the sunspot activity does not track exactly between the northern hemisphere of the sun and the southern hemisphere. They follow a little bit of a different drummer. And this complicated chart, I just have you focus on the dark blue line that tracks along the top, that curve tracks along the top. And then the purple line, which is the southern hemisphere sunspot number. And then the kind of turquoise line down the bottom, which is the northern hemisphere. So what you can see here, this was for the last sunspot cycle 24. And what happened in sunspot cycle 24 is that the southern hemisphere of the sun had a lot more sunspot activity than the southern half. And you can see that in the purple line, how the southern hemisphere was pretty quiet in 2012 and 2013. And then it took off like a rocket ship towards the end of 2013 and produced a lot more sunspot activity. And why is this important? That appears to be exactly what's happening right now. If we were able to extend that turquoise line up into 2024, we would see that it's kind of started to slough off, just like the turquoise line sloughed off in 2012. But the purple line, the southern hemisphere line, has taken off like a rocket ship, just like it did in 2013 and 2014, but even more intense than it did back then. And this is what has caused 10 meters to be so good. And 12 meters is open till almost midnight, most nights. And 15 meters is open all night. We did not experience this 11 years ago. We did about 22 years ago. So what is this mess? These lines, these curves, show the sunspot number for all of the sunspot cycles since they started counting them about 150 years ago. And they're synchronized to each other so that their solar minimums track each other. So each one of these lines begins at solar minimum for that sunspot cycle, where it says 0 on the left side. So what you can see from this chart is an interesting aspect, and that is that the more powerful solar cycles, the ones that have big numbers that go very far towards the top of this chart, notice how they climb to those high sunspot numbers very quickly. In 3 or 4 years, they reach their maximum values. And the weaker sunspot cycles, and the classic one is the last one, which is sunspot cycle 24, labeled SC24, they climbed very slowly. Well, sunspot cycle 25, the one we're in right now, it's kind of shown. It's kind of shown in those in that black solid heavy line, and then the dots for the forecast. It started to rise fairly slowly. I mean, clearly it doesn't fit the very powerful cycles that climbed way up to 250 or almost 300. But it's suddenly started to rise this summer, so it's going to be more like sunspot cycle 23 in the green, or maybe even like sunspot cycle 22. Only time will tell. And the nominal time from solar minimum to solar max is 53 months. And that's just about where we are right now, almost exactly. And this is just another way of showing that the northern and southern hemisphere of the sun have different sunspot cycles. Some years they track pretty close. You can see for cycle 21 on the left side that there was kind of only one peak. But solar cycle 22 had 2 peaks. Solar cycle 23 had 2 peaks. The last sunspot cycle 24 had 2 peaks, and the second peak was much more strong than the first one. And the same thing is happening in sunspot cycle 25. The second peak is much stronger than the first one. Another aspect of the sunspot cycle, you remember early in my presentation, I said that there are 3 primary things that affect HF radio propagation. One is sunspots. One is magnetic activity, and that originates from the sun, not the Earth's magnetic field, but the sun's magnetic field. And the seasons. Well, the seasons carry on, so they don't get affected very much, but they have a big effect overall because the northern hemisphere, when it's pointing towards the sun, gets a lot more radiation, just like we do in the middle of the summer. So what happens during solar maximum is the sunspot activity that we just showed tends to peak at solar maximum, and that's shown in that vertical purple dashed line, 2024. But the magnetic activity coming from the sun, and that causes bad propagation, disturbed propagation. That tends to peak about 2 years after solar maximum. So we get more of the bad days over the next couple of years than we did going up towards solar maximum. We've had relatively small number of badly disturbed days, but they're starting to be more frequent, and they will be even more frequent over the next couple of years. But there's good news here, and that is because the sunspot numbers are so high right now since July, it tends to wash out a lot of the bad effects of the enhanced geomagnetic activity. So they kind of balance each out for the most part. So the effects are not as severe as they might otherwise be. So we'll just take a quick look at some of this stuff on the sun. These are The little short video clip on the right shows a sunspot, and its surrounding area on the sun. And the closed magnetic field causes the area in the center of the sunspot to be cooler. And that's what causes this black area in the center. So that's cooling caused by the intense magnetic field activity there. And looking in the lower left-hand corner of this slide, you can see a little video clip showing sunspots as they move across the surface of the sun. So they change, they don't stay the same. It's not unusual for them to strengthen as they move across the sun. Depending on where they are in the life of the sunspot, sometimes they weaken as they roll across the surface of the sun. Some sunspots only last for a few days or even less. Others last for several months. But remember that the sun, just like the Earth, is rotating, but it rotates once every 27 days. So these very powerful sunspots, like some of the ones happening right now, as they rotate around the sun and then rotate around to the backside, they'll still be there when the sun comes back on around. And we get to enjoy those powerful sunspots for maybe 2 rotations of the sun, sometimes even 3 rotations of the sun. And in terms of the size of sunspots, in the upper left-hand corner is just a snapshot, and imposed on that image is an image of the Earth on the same scale. And this one of the largest sunspots ever photographed is actually bigger than the surface area of the Earth. They're quite remarkable. I'll show you in a little bit an image of a coronal hole, but the coronal holes are areas of open magnetic fields that extend. They cause the sun's magnetic field to extend throughout the solar system. And as the sun rotates, it causes a complex interaction among the magnetized particles that are escaping the sun through these coronal holes. And this is just an illustration that shows that. Sometimes I like to refer to the sun as kind of a sailboat in a vast ocean. The vast ocean being all of the radiation from the sun, and the Earth is just this tiny, tiny little object in this vast ocean. And it experiences tremendous variability caused by the sun, and the rotation of the sun is a big part of that. These 27-day cycles I mentioned earlier. And this is just an illustration. The radiation of particles from the sun, not electromagnetic radiation, but particles form something called the solar wind. And the speed of the solar wind is just astounding. It's just numbers that are hard to put your hands around, but it's hundreds of kilometers per second is the typical wind speed we're talking about. And turns out most of the energy in these particles is in their tremendous speed, not so much the energy in the particles, and that's very significant. But the speed of the solar wind is where the greatest part of the variability is. And the stronger the solar wind is, the biggest its impact on HF propagation. This website has some interesting graphics and actually videos that show how the solar wind varies with time. And it's kind of interesting to look at this. Unfortunately, I don't have a video of it. But in the lower right-hand corner shows the velocity of the solar wind. These crazy numbers that are hard to put your hands around. 300 kilometers per second, or in this chart 450, but the numbers can even approach 1,000. Very rare. So this shows the variability of the intensity of the solar wind over time, and it varies over a period of minutes to hours to days. So coronal hole high-speed streams originate from these things called coronal holes. So, and I'll show you an actual image of a coronal hole in a moment. But the important thing to remember about coronal holes is that they are areas of open magnetic field. So in that illustration in the upper left-hand corner, the coronal hole, the magnetic field, if you just follow my cursor, they extend far into space to the Earth and way beyond to the edge of the solar system. And this is where these particles escape from the sun and are propelled into outer space at velocities of hundreds of kilometers per second. And illustrated here is sunspots with the magnetic fields that are closed, and these dark areas where the surface of the sun is cooler. And by surface, I mean the visible surface. The sun is gas, so it doesn't have a surface like the Earth. So this is an image of a coronal hole. And this image was shot at solar minimum. And it's huge. I mean, it occupies maybe 10% of the surface, visible surface of the sun. So this, during solar minimum, this unusually large coronal hole allows megatons per second of highly charged particles to escape the sun and cause all kinds of mayhem with propagation. And this is mainly a problem at near solar minimum, so we won't see a lot of this for quite some years. There are still coronal holes on the sun, but they're much smaller during solar maximum, so the solar wind is not as disturbed, not as powerful. So the effect of these particles accelerated at massive speeds from coronal holes, their primary effect on propagation is what is called a minor geomagnetic storm. And you know, these minor geomagnetic storms occur throughout the sunspot cycle. They're happening now, but we hardly feel any effect for them at solar minimum, at solar maximum. And the reason is that the beneficial effects of the sunspot cycle tend to wash out the effects of minor geomagnetic storms. But when we get to solar minimum, when there isn't as much beneficial radiation from extreme ultraviolet light, in other words, from sunspots, these coronal holes take on a whole different significance. And they cause some very, very bad days during solar minimum when we have a minor geomagnetic storm, but very little ionization. And the HF bands can really be very severely affected, even though the storm is called a minor storm. Well, during solar minimum, we very rarely get any strong geomagnetic storms. They're very uncommon during solar minimum, and they're much more common during solar maximum. And this is what causes the effects on propagation during solar maximum. So what causes all this stuff on the sun? Well, remember the sun is rotating every 27 days. So it's spinning on its axis, and it has to spin a whole lot faster at the equator for that to keep up. You know, it's sort of like being on a racetrack, where if you're in the outer lanes, you have to be traveling a whole lot faster than in the inner lanes, and the same is true on the sun. The spin is much slower on the poles, and it's very, very fast near the equator. And this causes the magnetic field of the sun to get twisted. And it's the effect of all this twisting that causes our sunspot cycle, the 11-year cycle. Nobody knows why it's 11 years. That is one of the great mysteries of solar physics, is why it's this an 11-year cycle. And I don't know that we're very close to having an answer to that. But it's one of the most observable features about the sun, but it's a total mystery. So this is just an illustration of the sun. It's tilted the sun is tilted 7 degrees. Remember the Earth and our seasons, that's caused by the Earth's 23.5-degree tilt. Well, it turns out the sun is also tilted. So this also contributes to the seasonal aspect of the relationship between the sun and the Earth and the seasonal effects on HF propagation. This 7-degree tilt has, I would say, no effect on the weather conditions on the Earth, but the 7-degree tilt has a big effect on radio propagation because of the sun's magnetic field that extends all the way out through the solar system. So the magnetic field of the sun, very, very intense magnetic field, is tilted 7 degrees. And this is a look at a couple of the events that we see very commonly during solar maximum. On the left side is an explosion associated with solar flare. And solar flares are very, very common during solar maximum. We see many of them every day. And solar flares are kind of a very broad effect. So when they explode from the sun, the chances are, if you can see a solar flare on the surface of the sun, which you can from a telescope, then it's going to affect the Earth. On the other hand, much more powerful explosions are known as coronal mass ejections. But the chances of a coronal mass ejection hitting the Earth are pretty slim, but not zero. So when the Earth happens to be in exactly the wrong place at the wrong time, and one of these coronal mass ejections hits the Earth, its effects, a very strong coronal mass ejection, its effects can last for days. And it can shut down power grids. It can force the shutdown of oil pipelines, of gas pipelines, or these very large features on the Earth can be badly affected. Very large, you know, it's very unnatural on the Earth to have very long metallic structures that extend for thousands of miles. It's a very unnatural thing. And when you put these huge conducting structures like pipelines and long distance power transmission lines, they get severely affected by these coronal mass ejections. It can even cause these huge transformers in some of these lines to catch on fire. The first one that was noticed to any significant degree was something that is called the Carrington event. That was the name of the astronomer who noticed it when it was going on. And the Carrington event caused some of the telegraph stations, and of course, telegraph was a brand new technology in the middle of the 18th century. It caused some of these telegraph stations to catch on fire. Telegraph at the time operated with batteries. And during this Carrington event, the telegraph operators discovered they didn't need a battery. The long distance of the telegraph lines got charged during these this huge coronal mass ejection, and they didn't need batteries at all during this event, assuming they had a telegraph station at all if it didn't get burned down. So solar flares are relatively short duration events. They usually last only an hour, often less than an hour. Most of them don't last more than 2 or 3 hours. So what are they? Solar flares are explosions of electromagnetic energy. It's not particles, and it's the most important radiation from solar flares is X-rays. And what X-rays cause is absorption in the lowest layer of the ionosphere, extreme absorption in many cases, so that it shuts down the ham bands. If the solar flare happens to be on the side of the sun facing the Earth, it can shut down the ham bands from anywhere from minutes to hours. Well, the ones that last minutes, most of us don't even notice that. You know, we're kind of used to the variability of HF. We don't worry about that too much. But the ones that last for hours, we notice. And if you talk to some old timers that spend some time on the air, there'll be some occasions where they turn on their radios and it appears like the radio has failed. It's the effects are just that severe. And some people start to debug their radios, try to figure out if their transmission lines to their antennas have failed. And it turns out, no, basically the ionosphere failed. One of these intense flares caused extreme absorption in the D region of the ionosphere, and there was no possibility of propagation. I've experienced a number of these myself, and during the flare, you could only hear local stations that didn't need the ionosphere for communication. So you could hear your friend 10 or 20 miles away. You could probably hear him better than ever because all of the interfering signals that come through the ionosphere were gone. And the only thing you hear on the 20-meter band was people in your own city or maybe the next city, and that was it. So if you ever hear anyone talk about, and these things, by the way, are called radio blackouts. If you ever hear anybody talk about solar flare effects at night, it's not possible because the electromagnetic radiation doesn't affect the night side of the Earth. Our location on the Earth has to be facing the sun for this electromagnetic radiation to have an effect. It doesn't cross over into the night side. So these effects are exclusively daytime effects. Now, from an HF point of view, of course, we often want to communicate with someone halfway around the world. So that propagation path might be in an area that's in daylight. And if that's the case, it could be affected by one of these flares. So I think I've already talked about this. Most of these very strong solar flares, and they're called X class. They usually, but not always, but usually occurred near solar maximum. But this big Carrington event that caused some telegraph stations to burn, that occurred about 4 years after solar maximum. So it isn't. These don't occur only at solar maximum, but they occur much more frequently near solar maximum, right where we are right now. There's another kind of an absorption event, but it's very uncommon. It's called a polar cap absorption event. They tend to be associated with very strong solar flares. They usually only occur, the strong ones usually only occur a few times a year. I think the most recent one that I noticed was back around June or late May. And this map kind of illustrates what's going on. It only affects the poles. The explosive event from the sun carries protons at very high speeds, about 1/10 of the speed of light, which is incredible for a particle. And when they reach the surface of the Earth, they get directed to the polar regions by Earth's magnetic fields, and they can cause total blackouts of propagation, forcing the poles. And this particular graphic illustrates what happens to propagation in the southern hemisphere of the sun during the southern hemisphere summer, when one of these polar cap events occurs. Most of us will never notice one of these. They're infrequent, and they only affect propagation coursing the polar region. So from North America, that would be propagation into Siberia, for example, or into China. And it can be inexplicably shut down, and it gets caused by one of these events. I've already said everything I want to say about these strong polar cap events. So these coronal mass ejections, illustrated on the left-hand side, we're going to continue to see those for a couple more years, probably 2 or 3 more years, and then they'll start to become less frequent. But over the next, even though we're at solar maximum now, and we're going to start declining out of solar maximum sometime in the next 2 years, we're going to keep seeing these CME effects for probably 4 years. And I think I've said everything I want to say about this. Coronal mass ejections occur with different speeds, and it's the very high speed ones, so they're called fast CMEs that we mostly worry about. At this part of the sunspot cycle, we see frequent CMEs. At the bottom of the sunspot cycle, during solar minimum, we don't see very many of these at all. Thank God, because propagation is bad enough at solar minimum without having these events making it even worse. So there's another interesting aspect to this. So remember back when we were in elementary school, I think probably everybody in elementary school learned about magnetism with horseshoe magnets, maybe placed on a tabletop. And we learned if you oriented the north pole of one magnet to the south pole of the other, that they would attract each other very strongly. And if you oriented them opposite, so it was north on one horseshoe magnet to north on the other, they would push each other apart. Not as strongly, but still they would push each other apart, and you really couldn't push them together. As soon as you attempted to do that, they would push each other apart. Well, exactly the same thing happens between the Earth's magnetic field and the sun's magnetic field extended out into space along the solar wind. So, we're very fortunate on the Earth. We have a magnetic field, and it protects us from almost all of the severe effects from the sun. Mars, on the other hand, has no magnetic field, and exploring Mars is going to be a very dangerous proposition. But on Earth, we're protected from all this stuff, particularly on the surface of the Earth. Not quite as good if we have satellites orbiting the Earth, but on the surface of the Earth, we're very safe. Well, it turns out for these disturbances from the sun, such as coronal mass ejections, the way the Earth's magnetic field saves our lives on the Earth from these effects on the sun, when the Earth's magnetic field is oriented identically to the orientation of the magnetic field from the sun, the same thing that happened in elementary school with these experiments happens in the ionosphere. The magnetic field from the sun gets deflected away from the Earth, and even if there's a fairly severe disturbance from the sun's magnetic field, it gets pushed away and all is well. But only about half the time is the Earth's magnetic field oriented the same as the sun's magnetic field traveling throughout space. About half the time, it's the other situation from elementary school where the magnets are oriented opposite to each other. And turns out that that these powerful magnetic effects from the sun can infiltrate into the ionosphere. Fairly complicated process that I won't get into, but during about half the days when the orientation of the Earth's magnetic field is opposite from the sun, those are the days when we can get strong geomagnetic storms. And this is what makes it very, very difficult for people who forecast radio propagation to determine whether we're going to have very badly disturbed propagation. It's very difficult to predict reliably whether the interplanetary magnetic field originating on the sun is going to be oriented the same as the Earth's magnetic field or opposite. So when it's oriented the same, the Earth very effectively pushes that aside. But when it's opposite, those are when we get severe geomagnetic storms. And they can really affect propagation on almost the entire Earth. It's not quite so bad down in the equatorial regions. Even in the Caribbean, it's not as bad. But up near the poles or high latitudes, let's say Canada, Northern Europe, the effects are really bad when our elementary school experiment goes bad and these two magnetic fields get pulled towards each other. All of these protections we get as human beings on the surface of the Earth don't apply in the ionosphere under those conditions, and we get some really bad storms. So we've just touched upon the complexity of the sun and the Earth and their interactions. This just, in a kind of a cartoonish way, shows a whole variety of things that we currently understand about the Earth. That the object in the center there is the Earth's ionosphere, and all the different kinds of effects that happen on the Earth as a result of us being in the influence of the sun. And there are undoubtedly a whole bunch of things not yet discovered. I'm not going to talk about all these. This presentation would go on forever if I attempted to discuss all of them, but I have discussed the most important ones. So let's talk a little bit about propagation now. So we've talked about what's happening on the sun and how it affects the ionosphere, but let's get down to what's important, and that is, how does this affect us on the air with propagation? And these slides were written before July, before this sunspot cycle started to take off like a rocket ship. So some of the words that are used here are a little bit gentler than what has actually happened. So keeping in mind that this solar cycle really started to improve propagation a little less than 2 years ago, and it has gradually improved until July, when it started to improve very rapidly. The term I used in this slide when I wrote it was frequent 10-meter propagation. The correct term now is everyday 10-meter propagation is likely to continue through 2026. Of course, there'll be the occasional bad day, but 10 meters is open all day long now, and that's only going to get better as we get into the fall. And sometimes it's open until midnight. Not always, but sometimes. 12 meters 12 meters is a wonderful HF band. It's not as crowded as 10 meters. There's a lot more stations using simple antennas and 100-watt power levels on 12 meters. So it's a great band for a basic HF station to really have some fun. And that band is open with really strong signals every day now. And it's common for it to be open late at night. Now, the big difference in this strong solar cycle is that 20 meters, 17 meters, and 15 meters are open 24 hours a day, something we haven't seen in 22 years. And we don't know how long that's going to last. You know, it might start to degrade in 6 months, or it might continue for a couple of years. Only time will tell. But this sunspot cycle is going to go through its 11-year cycle, and eventually these good days are going to come to an end. So I've already talked about disturbances. They're going to become more common over the next couple of years, but eventually, as we approach solar minimum, they'll start to go away also. This slide was originally written for contesters, but that's all right. It affects everybody. One oddity about the summer affects 20 meters. And the more south you are in the United States, the more you see this. And that is, you might think, gee, 20 meters should be good day and night. But in the summer, 20 meters degrades pretty badly in the middle of the day in the summertime. So that's normal, and you expect it starting maybe around 9 or 10 o'clock in the morning. And the further south you go, like down into the Caribbean, the degradation in midday in the summer lasts even longer. And this is an everyday thing. It'll in our mid-latitudes in the US, most of this will go away around October, November, and then it'll be completely gone during the winter, and then it'll start happening again next May or June. So 20 meters in the summer is not a very good daytime band, but these effects do not have a significant effect on 17 meters and really no effect on 15 meters. So these bands are great in the daytime. And in the summertime, they're incredible at night. Even now in the summer, when 10 meters in a more moderate solar cycle, when 10 meters is not particularly good in the summer, this is such a powerful sunspot cycle that 10 meters is fine in the middle of the day. I was on 10 meters this afternoon, early afternoon, and there were stations from Indonesia coming through. There were stations from Africa, from the Middle East, from Russia coming through on 12 meters in the summertime. That doesn't happen in weaker sunspot cycles. And 12 meters was just incredible today. This slide was written before July when the sunspot cycle went wild. So now this worldwide propagation on 15 meters is happening every day. It isn't just September through May, because this sunspot cycle is so strong. 15 meters is just great in the middle of the summer, and it's open often after midnight. Well after midnight. I was on 15 meters this morning at 2 a.m. and it was wide open to Europe, 2 a.m. Probably stayed open all night long. But it's a fantastic band. And I've already talked about 20. At this part of the year, it's a fantastic DX band from late afternoon all through the night and into the morning hours until 9 or 10 a.m. when it starts to fade during the middle of the day. And 40 meters is at this part of this very strong sunspot cycle. It is a fantastic DX band all night long. From shortly after sunset all through the night, all the way to sunrise, and even for a while after sunrise, and then it shuts down and becomes kind of a local band where you can work from North Carolina to Tennessee or maybe Indiana, and that's about it on 40 meters in the middle of the day. And 80 meters is still a usable DX band, mostly during the winter, and mostly in the hours near midnight. So you don't expect to get on 80 meters during solar maximum and start to work DX at sunset and then through most of the night. It tends to be best during our midnight hours. And also to the Pacific tends to be best during the late night in those regions, like in Hawaii. Propagation to Hawaii is best around their midnight time, which is a few hours before our sunrise. And 160 meters, well, if you're not a really serious 160 meter DXer, this is a bad time of the sunspot cycle for 160. But it can be done. There's this big DXpedition that just wrapped up yesterday on Jarvis Island. And they made an enormous number of QSOs on 160 meters, but they were very, very serious. And they were mostly, well, they were using a lot of digital stuff and also very skilled operators on CW. So they made a surprisingly large number of 160 meter contacts. That's certainly much to their credit for having done as well as they did under very difficult conditions. Okay, so this is just about the end of the presentation. Forecasting HF propagation, it's very challenging. The sun does what the sun is going to do, and it's very difficult to forecast with a high degree of accuracy what it's going to do tomorrow or the next day, or especially next year. But now in the 21st century, we've got a lot of tools available to us that we never dreamed of 10 years ago, and they're available to us now. So we can use the power of the internet, and we all have computers on our desktop. So we can use these tools for something called nowcasting. So instead of relying on a forecast for what the bands should be doing right now, we can look at these websites and we can tell what the bands are actually doing right now. And not only can we see the fun that other hams are having, we can also get on the band and call a few CQs, and the receivers that are connected to these websites will detect our CQs, and we can tell where our signals are being heard now. So this is the reversebeacon.net website. You can't break these websites. So you just experiment with them. You're not going to break them. But for example, if K2TNO wants to see where he's being heard anywhere in the world on CW, Bill could just get on and call a few CQs and then go to this website. He can put his call sign in. It's on the right-hand side where it says spotted DX. So you put K2TNO in that block and hit the enter, and it will display all of these receivers all around the world that heard his CQ. And if it wasn't very successful, well, he can switch to another band and do the same thing again. And Bill can see where his CQs are being heard on whatever band he switched to. So this is a wonderful tool. It's worth learning how to use it. Very, very easy to use. It's also helpful, for example, if you're searching for the expedition, like the Jarvis expedition. Their call sign was N5J. So you could put the N5J call sign in on the right-hand side, and this will tell you where in the world they're having propagation right now, as heard by hundreds of receivers connected to this website. So I think the next one is my last slide. Yes, it is. This is another fantastic website. It's called pskreporter.info. And the power of this site is that there are thousands of receivers connected to it. Anybody who buys the software package called WSJT, when you load that package, you're given the option as to whether you report the signals copied by WSJT are reported back to this website. And almost everybody that uses WSJT checks that box. So then you've got thousands of receivers all over the world reporting all of the FT8 and FT4 stations that they're hearing. And you might say, well, I don't operate FT8, so this doesn't help me. Well, that's not true, because this is reporting propagation. So even if you never use FT8, it's still useful to know where the propagation actually exists in the world and whether it's in your area. And if you do operate FT8, you can do the very same thing with this website that you can with the one I just showed you, and that is you could put your call sign in, and you can call CQ, and you can hear where these thousands of receivers heard you all over the world. So this is my favorite way to look at propagation. It's not through forecasts at all, but using these nowcasting sites, either PSK Reporter or the Reverse Beacon Network, and there were some others too. There's DX Maps, for example, that displays the same kind of information. So I would encourage you, if you haven't tried these, to give them a try. Don't be shy.
Your comment?
Yeah.
Can I make a comment, Frank? So one thing people may not know about the PSK Reporter site is that in order to avoid broken calls, PSK Reporter for digital, for FT8, for example, just assumes that your transmitter is correctly sending your call and your grid square. But it will also do CW, but only if you send the following sequence: DE, call sign, call sign. If you send CQ, DE, K2TNO, K2TNO, that they'll find. If you send just DE, K2TNO, they will not, because they're worried about getting distracted by broken calls. Thanks, and I'll stop.
Okay. Very good. So there's just one other comment I want to make about another tool that's really very powerful. And it's called DX Alert. And this allows it does the same kind of thing you're seeing here, except if it can alert to a particular call sign that you might be interested in. Let's say, for example, the N5J expedition that just finished up yesterday, or maybe someone who's not very active at all that you would really like to make a contact with. Let's say JT1 in Mongolia, or a D2 station in Angola. You could plug the call signs into that alerting system, and it will either call your cell phone, but what I use and what most people use now, most of us have smartphones, and you can put an app on your smartphone, and it will send a Morse code alert to the app on your smartphone and tell you that a station you're looking for is active. So that's another really powerful tool, and it's quite a new tool, and it's really worth learning how to use. Okay, so that's the end of my presentation. Bill, can I send you a copy of these slides? And then if any of the members of the club want they can obtain it from you.
Yeah, absolutely. That's great, Frank. This was a fantastic presentation. Let me turn it over now to people who want to ask you questions. And most of you, I think, have got your audio muted. Just go right ahead and unmute, and then just do like we do on the net. Just say "this is," and if nobody is interfering with you, go ahead with your question. Thanks again, Frank. This is fantastic. Okay, standing by. Anybody has a question?
KR4LO.
Yeah, go ahead, Bill.
Yeah, I'd like to thank Frank very much for taking time out of his schedule to give us this nice presentation. I thoroughly enjoyed it. Thank you very much, Frank. KR4LO.
You're very welcome, Bill, and take a look for my article coming up in the next issue of QST.
Nice.
I think you'll find it very informative.
So I've a question, Frank. Could you talk a little bit about the ideal locations in the across the globe at various portions of the day? For instance, we live here in the mid latitudes. What should somebody, other than looking just to see what happens to be working, are there any obvious places that we should make sure not to avoid?
Well, I'll tell you, in my opinion, the very best place to live is at mid latitudes. If you ever go on a DXpedition into the areas near the equator, they have all kinds of nasty effects we didn't even get into in this presentation. And it's even worse when you get up into the areas near the poles. Our poor brethren up in Canada have a lot more severe effects from these coronal mass ejections than we do. So if I were to pick up an ideal place, I might say North Carolina.
You're right.
You want to buy some land?
That's a really good place to be. Some hams have been investing a lot of money building ham stations up in Maine. You might be aware of that. There's some really huge ham stations built in Maine. And they have the advantage of being close to Europe. That's the main thing. Europe is just a stone's throw across the pond from Maine. But Maine is badly affected by disturbances to the magnetic field. So they have some really, really bad days also. Days that hardly affect you at all in North Carolina can shut down HF propagation up in the far northern areas of Maine where some of these big stations have been built. So I think I'd stay in North Carolina.
Okay, I've done that for you. I'm going to do that. Frank, another quick question. Have you noticed with your big antenna farm, during various types of propagation situations, do vertically oriented antennas or horizontally oriented antennas on various bands, is there any sense that one is better than the other at various times when propagation is not just state of the mill?
Okay, that's a really good question, Bill. Thank you. So from a pure propagation point of view, the only band that is selective to propagation is the 160-meter band. The 160-meter band, from the perspective of hams in the United States, favors vertical polarization strongly over horizontal, both from a propagation perspective, and this is because of the Earth's magnetic field, but also from an antenna performance point of view. A 160-meter antenna that is what's the highest antenna you would ever consider putting up, maybe 70 feet high, horizontal, inverted V. Nice convenient antenna to put up on a tower if you got enough room. So you've got a 160-meter inverted V at 70 feet. Well, that's like having a 10-meter horizontal antenna at about 8 feet. And anybody who's tried to use a horizontal antenna on 10 meters that very close to the ground, they just don't work well. Because what happens is to the radiation has nothing to do with propagation at all. It's just that an antenna that close to the ground radiates straight up when it's much less than a quarter wavelength above the ground. And it's really, really hard on 160 meters to get an antenna much higher than a quarter wavelength high. 160 meter dipole, a quarter wavelength high, is 140 feet in the air. And it's still a very poor DX antenna. So anyway, bottom line to the answer to your question, from a propagation point of view, everything is equal except on 160 meters. The ionosphere doesn't care about polarization. And let me just amplify on that in a slightly complicated way. And I won't get into the details as to exactly why this happens. But anybody who's active on the HF bands has noticed that unlike 2 meters, for example, on 2 meters, if we are using vertical polarization, let's say with a whip on our vehicle, and we try to communicate with someone using horizontal polarization, it doesn't work very well on 2 meters. It doesn't work very well at all, and it gets even worse higher. But on the HF bands, this doesn't happen. When we communicate via the ionosphere on 80 meters, 20 meters, 10 meters, doesn't matter what polarization we use, our antennas just work. We don't have this cross polarization problem. And why is that? Very simple. It has to do with the Earth's magnetic field and its effect on the ionosphere. When an HF signal on any of the handbands in the HF range, including the 160 meter band, when they enter the ionosphere, the magnetic field of the Earth causes the polarization of that signal to become elliptical. So there is no such thing as vertically polarized propagation through the ionosphere or horizontal polarization through the ionosphere. It's all the same, except on 160 meters, where the ionosphere tends to absorb vertically, horizontally polarized signals, in addition to antennas just being too low. So when that signal comes back to the ground, if it started out vertically polarized, by the time it gets to the far end on every band except 160, its polarization is constantly changing between vertical and horizontal. So we don't care. So
Gotcha.
what it comes down to, go ahead.
No, go ahead, Frank. Sorry, didn't interrupt.
Okay, so from the point of view of the ionosphere turns our vertically polarized signals or horizontally polarized radiation. It turns it into elliptical. So it doesn't matter. So what does matter? It's the same concept as with 160 meters. What we care about is antenna efficiency. So this isn't polarization at all, it's antenna efficiency. So what we want to be sure that we don't do is to waste any of the radiation coming from our antennas to be wasted heating up earthworms. That doesn't help us communicate with the people we want to communicate with. We want to be sure that that effect is as small as it can possibly be. And it turns out that horizontally polarized antennas, more than about 2/10 of a wavelength high, are almost 100% efficient, regardless of whether they're over the ocean or over a sandy desert. Very, very little difference in efficiency, less than 2 dB. So horizontally polarized antennas are what you want to use unless you can't get them high enough. And my article in QST next month addresses this topic of basic antennas for the HF bands. And it turns out that roughly a quarter wavelength high, preferably a little bit higher, horizontal is the polarization you want to use. So let's say for 10 meters, a quarter wavelength is 17 feet. So I'm sorry, it's 8 feet. Half wavelength is 17. So on 10 meters, a quarter wavelength is 8 feet. And what we really would like to do on 10 meters is get our antennas about 20 feet high. And then they start to work very well. That gives us better low angle radiation. And of course, if we raise them even higher above than that, they're even more effective. But from an efficiency point of view, when we get a horizontally polarized antenna about a quarter wavelength high and higher, the efficiency is very close to 100%, regardless of how bad our soil is. But that's not the only consideration. If you live in New York City in an urban canyon, you're going to have a problem no matter what, because all these big buildings are going to cause a serious problem. So you've got to try to get your antenna out of the canyon. And a similar thing happens if you're in a very crowded suburban neighborhood, you know, where you can open your window in the middle of the night and talk to your neighbor in the house next door. A very crowded suburban neighborhood, you really should try to get your antennas up above the congestion. So that the electromagnetic field from your antenna isn't mostly just lighting up the electric wiring and internet wiring and cable TV wiring and all the other stuff in the congestion. So you like to get your antenna up out of that. And the only other situation that is somewhat of a compromise, but it's not terrible, is that HF antennas of any kind don't work very well in a very dense forest. And here I'm not talking about just a few trees in the neighborhood. But if you find a very dense forest and you try to put your HF antenna in the middle of that very dense forest, it's not going to work very well. And this is one of the reasons that NVIS antennas were invented, near vertical. And that is, if you get the energy to escape the forest as fast as it can, and that means straight up vertically, then the problems of operating in a jungle are not so bad. But if you try to propagate from the middle of a jungle or from the middle of a very dense forest down to the horizon, you've got a big problem, because you've got a whole bunch of trees and a whole bunch of other stuff very low that your signals are trying to get to, and that gets to be a problem. So this is a very complicated question to answer to a very simple question. And that is basically from a propagation view, except on 10 meters, it doesn't matter. But from an antenna point of view, horizontal is preferred if you can get it high enough, which generally means more than a quarter wavelength high and not in the middle of an urban canyon.
Frank, this has been great. Let me open it up for just a couple, if there are any more immediate questions. Otherwise, I want to gavel this to a close. Anybody turn your audio on and ask a question if you have one. Yeah, go ahead, Jim.
At the outset, before we were interrupted, I guess, the comment had to do with 6 meters. Now, I know that's not HF in this case, but it was broached. And yes, I do use or used to use 6 meters. My question, Frank, if you are a user, what's going on? This season, as far as I'm concerned, has been terrible.
Yeah.
And it's particularly worse if Dick had to drop out. I understand that he had to leave, but he too has come up with that same observation. And
Yeah, and you're not alone. If you talk to anybody who's active on 6 meters this past summer, when usually we get at least some sporadic heat propagation over very long distances, that's been almost non-existent this year.
that's right. And I see the parallel, however, with peaks and sunspot cycles that 6 meters does not perform as it is expected to do. And you don't see it track so much with the sunspot activity as the other bands. The nice thing about 6 is it has, you know, the features of both, like 10 meters does. And sometimes 10 meters will give you some E-prop.
Yep.
But, you know, it is an up and down situation with 6. Now, that all said, we talk about North Carolina being a great place to live for HF. And yeah, I think if you remember, VOA had a few sites here in the.
Oh yeah, I visited them. Yep.
And
Are they all shut down now?
one's still operating.
One is still there. I've been at that site, the one that's still running. Yeah.
Yeah, Site C, I believe it's called.
Yeah, that's right.
That we are also in a black hole for 6 right here. For some reason, this part of North Carolina, you just can't get out unless the conditions are great. So that's the way it is.
Here's the answer to your question on this slide. You see this slide?
Yeah.
Forget everything you know about HF propagation.
Right. Totally agree.
Doesn't apply to this band. And the primary reason, of course, is except during very strong sunspot cycles, we rely on sporadic E,
right,
and long distance sporadic E for all of the joy that we have on 6.
That's right.
Jen, so let me jump in.
If you don't have that little cloud around, Frank, you're not gonna get anywhere. That's for sure.
That's right. That's right.
Yeah, I miss those days with triple hop and all the rest, but that's the way it goes.
But you know, but don't give up. I'm pretty active on 6, and in the middle of July, I was doing something on the ham shack. I don't remember what. And I noticed I actually used this website, and I noticed that there was propagation from the East Coast to Japan on 6 meters.
Right.
Whoa, this is a wonderful website to use if you're a 6 meter operator, because it really tells you what's going on. And that's how I detected it. And I worked about 24 Japanese stations 6 weeks ago, I guess, on 6 meters. And without this website, I never would have known that band was open. But it was a really marginal opening. I could work, let's say, 2 or 3 Japanese stations, and the band would die.
Right.
And it would stay dead for about 5 minutes. And suddenly it would open again, and I could work 2 or 3 more, and the band would die. And that happened 4 or 5 times before I finally said,
Jenks,
my fun needle is pegged.
Jenks, let me jump in real quick here. Frank has been very kind to stay for a half an hour after his talk. And he actually has a lot to say about 6 meters. Let me offer the following. Frank, if you're willing to just chat for a few more minutes about 6 meters, maybe the people who are interested in discussing that with you can stay. Other than that, I'd like to shut this opportunity down. And particularly, I want to thank you, Frank, for a very fascinating story. And really, really nice of you to come and share your knowledge with us tonight. So let me turn it back to Frank for any comments. And then if anybody would like to stay around, and Frank, if you're willing to stay and talk for a couple of the guys about 6, that'd be great. But let's let you have the opportunity to get out of here.
Okay, well, I'll stick with it for a little while, not a whole lot longer.
Okay, and are there any other comments about Frank's presentation?
I
All
do
right.
have one comment, Frank. If I too am a fan of PSK Reporter, and I've found too a little secret that a lot of folks don't realize is that you can put in your target DX station or whatever, particularly if he's using WSJT, and you can pick up what he's seeing. So you not only can see where your signal is going,
Yep.
you can see where his signal is being
Yep.
received. So
Okay.
therefore, you have a very good idea when to shut down.
Yep, and of course, as you know, being an experienced user, you can select sent by, heard by, or sent and heard by. So you can do
Right.
it all three ways. It's a very powerful tool.
I love it.
How do
And
we ever do this ham
We
radio?
don't have to stick around for 6 meters on my behalf, but it's been great to talk to you about it.
Okay, so nobody knows with any certainty whether we're going to get F2 propagation this fall, but it looks a whole lot better than it did last year.
Cool.
Ever since and what happened is the southern hemisphere of the sun came to life just like it did 11 years ago, but even more powerfully than 11 years ago. And there's a real opportunity here that if the sun keeps up this activity for another 6 weeks, that we might have a really good time. And there's a big difference between F2 propagation and the sporadic E, because the F2 propagation is not sporadic. So when we get these openings, they can last for hours.
Yeah.
Let's let the good times roll.
Good call.
Yeah. So and there's nothing, we just have to be alert to this possibility, and tools like PSK Reporter mean that allow us to be aware of what's going on without having to glue ourselves to the radio. You remember back at Bill, K2TNO, you remember back in 1957, if you were a DXer, you had to sit in front of the radio hour after hour after hour.
Got
And,
that right.
we don't have to do that anymore. It's still fun to do it, but we don't have to do it anymore. So we've got all these tools that allow us to let our computers and the internet help us. And we couldn't do that in 57. We had to use our own ears and a button chair.
Oh, any other comments? Okay, Frank, I want to thank you very much again for everything you've done here for us tonight. And I want to turn down the recording, and everyone else, everybody's free to go. Thanks, everybody, for attending this. Frank, I can't thank you enough for how informative this has been.